What's that? Yeah, you're trying to calculate the 48.8 grams. What's that? Yes. It boils at a very low temperature. Yeah, this is only about 70 Kelvin above absolute zero. So what? It's when nitrogen starts to boil. That's why most of the nitrogen around you is gas. Not necessarily. It's all over the place in terms of melting points and boiling points and vapor. It's more of you have to do physical chemistry, which is applied electroquantum dynamics to figure out what a lot of these properties are if you don't want to do it empirically. It's fun stuff. Okay, so for this one right here, where I begin my solution, if you check it out at some point, one of the things that we said is since energy is conserved, then the amount of thermal energy exchange in the aluminum plus the amount of thermal energy exchanged in the nitrogen should come out to be zero. And when something is changing temperature, such as the aluminum is right here, that would be the mass of the aluminum times the specific heat capacity of the aluminum times the change in temperature of the aluminum. And that's going to be plus, so let's indicate that these three terms right here are the thermal energy exchanged with aluminum. And then the mass of the nitrogen, which you're trying to solve for, times the latent heat of vaporization for the nitrogen should come out to be zero. And if you solve for the mass of the nitrogen, you would end up getting negative mass of aluminum times specific heat of aluminum times change in temperature of aluminum divided by the latent heat of vaporization for the nitrogen. And if you're looking at this question, how did we get this right here? We said for anything that is, one of the things we talked about last time on one of our slides, anytime something is changing temperature, the amount of thermal energy exchange there is equal to, this was just an identity that we stated early on Thursday of last week. Okay, so back to my question. There's a negative out front there, which would indicate maybe that we've got negative mass that we're dealing with in terms of the nitrogen. So what's going on here that I'm not presently accounting for that would give us that the mass is not negative? The change in temperature is negative. So I have a negative out front here times a negative change in temperature. The negatives cancel, and I end up with a positive value for my aluminum. And so you could go through and double check this to get the mass of the nitrogen. A 100-gram piece of copper is heated in a furnace to some temperature C. The copper is then inserted in a 150-gram copper calorimeter containing 200 grams of water. The initial temperature of the water and calorimeter are 16 degrees Celsius, and the final equilibrium temperature is 38 degrees C. On top of this, When you've done everything, you find that 1.2 grams of water have been found to have evaporated. So what is the temperature T sub C? What is the temperature T sub C? Well, one thing that you'll want to consider here is the specific heat of copper is 0.386 kilojoules per kilogram per Kelvin. The specific heat capacity of water is 4.184 kilojoules per kilogram per Kelvin. And the latent heat of vaporization for water is 2,257 kilojoules per kilogram. And let's see here. You have a couple things going on here. You have 4 different thermal energy exchanges. You have the hot bit of copper that is superheated, that is cooled down, so that's one thermal energy exchange. When the copper that comes out of the furnace cools down, you have the water heats up from 16 degrees C to 38 degrees C. You have the calorimeter does the same thing. It goes from 16 degrees C to 38 degrees C. And then you have 1.2 grams of water that is vaporized. So 4 thermal energy exchanges. And if you add each one of those 4 pieces up and set them equal to 0, since energy is conserved, you should be able to calculate what T sub C, the temperature of the copper that comes out of the furnace, happens to be. So you got 4 things here, but only one unknown. That's T sub C. And don't forget that for the calorimeter, for the water, and for the copper that's coming out of the furnace, they don't all necessarily have the same delta T. So be aware of that as you guys, again, either work in pairs or groups or however you want to, and see if you can't give this one a stab. The correct answer that you should get is T sub C comes out to be 618 degrees Celsius. So y'all give this one a stab. I'll float around and we'll reconvene in about 5 to 10 minutes. four-person split screen on 4 different screens. And so you had your team on this one split screen, another team on this one, and it was all connected by LAN, and it was great. Well, you could look at your teammate's screen and know where they were, but you couldn't screen look on the others. But yes, if you're just playing split screen, just you and another friend against each other, screen looking happening. It was right there.
There was like people's rock bands too, right?
Yes.
Yep.
The days back before everything had to be played online. Harder problem? Unfortunately, this chapter, there's just not a lot of element to it. We started about entropy and thermal processes here in this class. That's when sometimes you have to pull out and things like that. Makes it, with these, yeah, if you keep algebra straight, or keep terms straight, fairly straight. So, we are doing heat engines, either today or Thursday. Yeah. All right, so with this one, if you look at my notes, maybe you do, maybe you don't. I've got the amount of mass here that is vaporized. I've got T of equilibrium, so that's T sub E. And then I've got the initial temperature of the calorimeter right here, mass of the water, mass of the calorimeter, except and then mass M sub 1 is what I call this one up here. And delta T is going to be 22 degrees C, which is T equilibrium minus T, T equilibrium minus T naught. And so if you look at the amount of energy for the block of copper plus the amount of energy of the calorimeter plus the amount of energy exchanged for the water plus the amount of energy that is used to vaporize here, then you get M1 times the specific heat of copper times T sub C minus T equilibrium. And then you get plus the mass of the calorimeter times the specific heat of copper plus the mass of the water times the specific heat of water times delta T plus the mass that's vaporized times the latent heat of vaporization of water equals 0. And you'll notice I lumped these two terms into this set of terms right here, considering that the calorimeter and the water both start and stop at the same temperature. So I just used the distributive rule to pull out a term of delta T off of each set of those terms. Okay. The last problem I'd like to look at is going to be the lead bullet. A lead bullet initially at 30 degrees C just melts upon striking a target. Assuming that all the initial kinetic energy of the bullet goes into the internal energy of the bullet, calculate the impact speed of the bullet. And this is really trying to get you to think about the mechanical equivalent of heat, right? That first law of thermodynamics. The first law of thermodynamics, which we stated, was that the change in energy, the change in internal energy of an object, is equal to how much thermal energy is added, plus the amount of work done on that system. Okay? So the change in internal energy is equal to the energy added by heat plus the work done on the system. And if you're struggling to know the difference between those two, the energy added by heat, imagine that you've got maybe some sort of flame underneath this, or you've got a difference in temperature that is causing a change in energy states. We have neither one of those in this problem, and so for this case, Q is 0. So it is up to us that if we want to find the change in energy of the system, that is going to be equal to, let's see here, the amount of, let's go somewhere else with this first. If we want to calculate how much work is done on this system, how would we calculate that? How much work, not on the system, but how much work is done on the bullet specifically? How would you calculate that based on the information given to us in the problem? Yes. Remember that work is equal to a change in kinetic energy, right? And in this case, we'll need the melting point, T melting of lead, is 600 Kelvin. The latent heat of fusion for lead is 24.7 kilojoules per kilogram. And the specific heat of lead is equal to 0.128 kilojoules per kilogram. And actually, I think I've got this mixed up here. Let's think about this. I'm trying to think. Absence of... I think the way that I need to be thinking about this specifically is actually... if all of the energy goes, the kinetic energy, I think this is where I messed up, all of the kinetic energy, which is associated with the work, goes into internal energy of the bullet. I think I'm boogering this up a little bit. Maybe the better way to think about it is to say that I'm trying to think. E initial is equal to K initial, so there's only kinetic energy, and then E final. No, I'm trying to think of a good way to explain it. I don't like the way it's written in my solution from last semester. So I'm trying to find a good way to explain this. That the total change in energy, I'm wanting to say that let me come up with a better explanation and talk about it, but on next time. What we end up getting is 1/2 mv squared is equal to m times the specific heat of lead times its change in temperature, and that's going to be going from 30 degrees C to, or since that's in Kelvin, that would be 303 Kelvin to 600 Kelvin, plus the mass of this times the latent heat of vaporization. And I'll try to come up with a better explanation before next class period, because I know I'm butchering that. But all this is saying is that the kinetic energy that it has is equal to the amount of energy that is exchanged via the thermal processes, but that's going from the kinetic. I'm really struggling here. It's a change in form of energy. If you think all the way back from physical science, like you can have chemical to mechanical energy or vice versa. This would be a mechanical to thermal energy exchange, I think is the best way I know how to describe it. So for this, the mass ends up canceling out everywhere. And you want to find the impact speed, so that means that V is going to be equal to the square root of 2 times C sub L delta T plus the latent heat of fusion, or that's 2 times 128 joules per kilogram times delta T. Delta T is going to be 297 Kelvin. Whoops. That would be joules per kilogram. And then you want plus the latent heat of fusion, that's 24,700 joules per kilogram. And that gives us 354 meters per second. So someone help me consider here that what we end up getting, and that's joules per kilogram per Kelvin, right there, sorry. Per Kelvin. Someone convinced me that the end result of this is a quantity in units of speed, unit of velocity, meters per second. How do I go from joules per kilogram per Kelvin times Kelvin plus joules per kilogram all the way to meters per second? Help me out and make sure that I've done my unit conversion correctly.
Is that fast enough?
What?
Is that fast enough?
Is it fast enough?
Yes, sir.
That do what?
Is that fast enough?
In this nice ideal world where the energy doesn't go anywhere else in the system, it's fast enough. But really, energy would go elsewhere in this problem. Yeah, Kai. It is, yes. A joule is kilograms meters squared per second squared. And so if you divide kilograms, right? So now you're just left with meters squared per second squared, which you take the square root of it, leaving you with meters per second. So yes, we are on the right track in terms of our unit conversion here. If we have time, we'll come back to this problem at the end of class, and I'll try to see if I've had any sort of enlightenment by then. Until then, or before then, let's actually switch gears and go into some new material, and then we can come back to that one if we need to. But y'all log on in, and we will get started here momentarily. You know, y'all put tragedy on here, which does make me a little bit sad, but I can't help but think of, instead of what you mean by tragedy and what Shakespeare meant by tragedy, and you've just got like Romeo and Juliet or Macbeth or something like that going on. But I'm sorry that you feel like physics was a tragedy to at least half of you here. Someone suggested in the other class that I should just combine comedy and drama to have a dramedy. Yeah, have you ever heard of a dramedy before? Oh yeah. What? A sci-fi comedy? Ooh, yeah, so Hitchhiker's Guide. Hitchhiker's Guide, yes, I know we've talked about that many times. If you've not seen it, it's a great thing. What? Horror, that's another one that gets commonly suggested, that people experience physics as a horror. I'm sorry that you feel that way. To me, it's an action thriller, and it's just so much fun. But I know I can only get so far with you guys. Let's dive in. Work done by a gas or work done on a gas. This is where now our definitions are getting so specific. That little preposition pair right there, by or on, is going to be incredibly important for the rest of this unit. It is important to know what is doing the work and what is receiving the work. If we're talking about work done by a gas, that means that the gas is doing the work. And if we're talking about work done on a gas, that means that the gas is receiving the work done. Seems insignificant, but it is still something that we need to consider. Last time, one of the things that we stated is that the kinetic energy of an ideal gas, an ideal monatomic gas, is 3/2 nRT. That would be, let me ask you this, is that the average kinetic energy, or is that the total kinetic energy? And what's the difference? This would be the total. Yes, this is the total. How do you know this is the total versus the average kinetic energy? Or maybe another way to say it, what would I need to change for this to be the average kinetic energy? Yes, when you're talking about little n, you're talking about moles, you're talking about the macroscopic property of the gas. So this would be total kinetic energy of all of the things in the gas. So if we could measure for every single gas air molecule inside of this classroom, if we could measure each one of the amounts of kinetic energy for every single molecule in this classroom and add up all of that energy, that's what we would get. Whereas if instead it was 3/2 times uppercase N times little k times T, that would be the average kinetic energy for what you would expect the kinetic energy for a molecule in this classroom to be. So there's a distinction. Make sure that you have that in your notes. It is important to note that if the internal energy is due to translational kinetic energy only, then the total kinetic energy is equal to the internal energy of the gas, which for an ideal monatomic gas, the only place you can store energy is in the speed of the molecules. So for an ideal monatomic gas, this latter case down here holds. Why is that important? Recall from pH 111, as much as you've tried to forget, that pressure is defined as what? Pressure is defined as what, Henry? Force per area. Pressure P is equal to F divided by A, right? Force divided by area. And work is defined as what? Oh, come on. We did this so many times in electromagnetic theory. Yeah, you integrate a force over some distance, that gives you work, right? And so what we're going to do is, you can see that there are forces here at play, force per area and force times distance, right? If we have force and factors of distance here, then we can maybe somehow relate them back to force that is applied here. So, if you don't like me just talking through what pressure and work are, there are the definitions we learned back last semester. And maybe you can get a feel for what's going, or what might happen here. Well, I don't want to skip ahead. We'll get there in a second. But pressure is force divided by area, and work is a force integrated through some distance. Just in case you've forgotten, someone remind me about the importance of the dot product there in that integral. Why should it be a dot product? For parallel components of the force and the displacement. That's right. So we only care about that if we're forcing something in one particular direction, that it is being displaced in that direction. Because again, work equals change in kinetic energy. So I'm trying to tie all of these together because in the image, we can imagine that the work done by the force F, which would therefore be the work done on the gas, is F times dx. But the force, we can relate to the pressure if we take pressure times the cross-sectional area of that piston. Okay? If pressure is force divided by area, then force is pressure times area. And in this case, the volume of the gas changes as minus the area times dx. Right? That is to say, as dx increases, the volume is decreasing. Therefore, work done on a gas is equal to the negative integral of pressure times the change in volume of the gas. So, according to this definition, if a gas is compressed, meaning that the volume is decreasing, that means there had to have been positive work done on the gas. Or if you cause an expansion, dV is positive, and you cannot cancel out your negative term out front here. So if you expand, dV is positive, the amount of work that you do on the gas is negative. who cares whether the work is positive or negative, right? Relate this back for me really quickly, what that means about the energy in the system. If the work on the gas is positive, that means we increase the kinetic energy, and that's the only place we store energy in an ideal monatomic gas. So by compressing it, we have, increased the energy within that gas. And if you expand it, you have decreased the energy in the gas. That's right. And if we've increased the energy, and the only place we store energy is velocity, then that means we have to increase the speed of the molecules in the gas if the energy increases. That's the kinetic theory of gases that we talked about last time. The pressure doesn't necessarily have to go higher. You can do it as an isobaric compression. There are certain ways that that has to happen, but you can do it. We'll get to that here in just a little bit. If work is being done on the gas and that work being done on the gas is positive, that means that dV has to be negative. The change in volume, the volume has to decrease. If the volume decreases, then dV is negative. Okay. Woohoo! Quick definition. A gas can undergo any sort of complicated process, but there are 4 particular cases on which we'll focus. If a process happens slowly, so that equilibrium is maintained, the state variables, let me pause there. Equilibrium is maintained, which is another way to say that the state variables are the same for the whole gas. State variable means pressure, volume, temperature, and molarity, if you will. So those 4 variables, pressure, volume, temperature, those are staying the same throughout the whole gas. So one of the questions we got last time was if you light a flame underneath a piston of gas, then you're going to get a part of the gas that is very hot right next to the flame and an area that is less hot, that the gas is non-uniform in temperature. But what we're saying here is we're doing processes so slowly here that they are what are called quasi-static processes, meaning that every time we change the state of the gas, we are changing the state over the entirety of the gas. You don't get fluctuations in the temperature, you don't get fluctuations in the pressure throughout the distribution of the gas. That if the pressure is 1 atmosphere at this point in the gas, it's 1 atmosphere over here, it's 1 atmosphere over here, 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 here. If it's 300 Kelvin at one place, it's 300 Kelvin everywhere. So you imagine if you very quickly compress this gas, what actually happens is you can get that all of the molecules that were close to the movable end of the piston are going to get a change in momentum very quickly. You get a higher pressure state close to the movable end of the piston and a lower pressure state further down. But if you do that slowly, then you change the pressure of the gas uniformly as you go. Just a quick idea. Did you have a question? State variables are, one way to think about it, the simplest definition are the variables that define a given state of the gas. And for us, for an ideal monatomic gas, that's pressure, volume, molarity, and temperature. Yep. Equilibrium means that thermal equilibrium is maintained, meaning that you don't have, that there are changes in temperature throughout the gas, right? That if we were to measure the gas at the top of the classroom while this classroom is being compressed, if the temperature is 300 Kelvin up there, it's 300 Kelvin down here. It also means force equilibrium, right? That the pressure is uniform throughout the gas. A state variable, another answer to your question, Maggie, is if you change the gas through some complicated process and return back to the same state, then you should have the same relationship between pressure, volume, temperature, and molarity. If those are, if they're the same throughout the entirety of the gas, yeah, then it's quasi-static. And if it's Quasimodo, then you've jumped into the Disney universe, and that's something different. Actually, I guess they got the story from a real life story, but still, I think of the Hunchback of Notre Dame. The simplest case for calculating work done on a gas is known as an isochoric, or you also hear it as an isometric process, in which the volume does not change. If volume does not change, then you have nothing to integrate over, meaning that the work done on the gas is zero, and delta E internal, the change in internal energy of the gas is just equal to the thermal energy exchange during that process. Where on earth does that last equation come from? How do I know that the change in internal energy is just the thermal energy added or removed from the gas? First law of thermodynamics. If a problem seems very difficult to you when you're solving any of these quasi-static process type problems, odds are it is asking you to give an application of the first law of thermodynamics, in which case delta E is W plus Q, but in this case W is zero, so delta E is just Q. Okay? If you look on your equation sheet, if you've got your laptop open or you've got a physical copy already printed out, you will notice a table of equations on there on the right-hand column, and all of those are relating back to the properties that you get based on the definition of the quasi-static process and how it relates to the first law of thermodynamics. That's all that complicated table of equations is doing for you, is it's summing up these next few slides into one single table and relating it to the first law of thermodynamics. The second process is called an isobaric process. This comes back to your question, Jacob. An isobaric process is one in which the pressure of the gas is held constant, in which case the work done on the gas is equal to minus P delta V. Work done on the gas is equal to minus P delta V. Where the pressure is constant, say 1 atmosphere, 2 atmospheres, or 30 atmospheres if you're in the Marianas Trench. Just a quick little side detour on your journey to the center of the earth. Okay. I feel like there was something else I wanted to say here. I think that's all I wanted to say. The next process is called an isothermal process, in which case the pressure is changing. And so what we get to do is an integral over path C there, where the pressure increases as the volume decreases. Well, what I can do is I can use the ideal gas law, since I don't know necessarily what the state of the pressure change is, unless I measure it empirically. I know from the ideal gas law that pressure is equal to nRT over volume. Well, nR and T are constant, and we're not expecting that we're draining off any number of moles of the gas, so N is constant, R is constant by definition, and T is constant for this problem because we said that the process was isothermal. The temperature is not changing. And so nRT can be pulled out front, and now we have an integral of dV over V, or 1 over x dx. And taking the integral of 1 over x dx, you get a natural logarithm. So the work done on the gas is equal to nRT times the natural logarithm of the initial volume divided by the final volume. But if you actually go through the calculus here, you'll end up getting log of a volume minus log of another volume. So how do I make the transition here that log of one volume minus log of another volume is equal to the log of the ratio of the volumes? Well, that's, yes?
That's like a logarithm property.
That's just, yeah, that's one of the identities that you learned way back in logarithms. If you have forgotten it, it would be worth refreshing yourself on it. But if you have log, and this, you'll hear me say log, it's a bad habit of a physicist. When physicists say log, they mean the natural logarithm. So if you have the natural log of A plus the natural log of B, then that's equal to the natural logarithm of A times B. And if you have the log of A minus the log of B, that's equal to the log of A over B. But what I would have gotten was the log of V final minus the log of V initial, but the equation said that this was the log of V initial over V final, right? Which would indicate that I'm taking the log of V initial minus the log of V final rather than the other way around, as is determined by my integral. How do I end up flipping the ratio here? Kayla? There was a negative out front of this. Don't forget the negative that is out front of the integral, which effectively would allow me to flip over the ratio here. Oh, and by the way, in this case, the amount of thermal energy that is pumped into the system is equal to minus the work done on the system. Where in the world does that equation come from? Where does the last equation come from for this system here? It again comes from the first law of thermodynamics, right? Because one of the equations we said last time is that the internal energy of a gas, well, we said this early on, right, is equal to 3 halves nRT. And so the change in internal energy would have to be 3 halves nR delta T. But what is the change in temperature during an isothermal process? 0, right? And so, if this is 0, because the change in temperature is 0, we said according to the first law of thermodynamics, that's equal to Q plus W, which is just equal to 0 for an isothermal process, or Q is equal to minus W, right? Every time these are coming back to the first law of thermodynamics. Okay? And so this is where you get really frustrated on an exam. And I'm warning you this because you'll also get really frustrated on your homework. So please hear me say this. You will get a question on the exam, maybe to this effect. Gas undergoes an isothermal compression from this volume to this volume. Calculate the amount of thermal energy exchange during that process. And you're like, my equation sheet doesn't tell me how much thermal energy is exchanged in the process. It only tells me how much work is done during that process. And what I'm trying to see if you understand conceptually is that, oh, well, if I can calculate the work done on the gas during the isothermal process, because I know that there is no change in the internal energy in the gas because there's no change in temperature, that means that if you want to know the amount of thermal energy that has to be pumped in, it's equal to minus the amount of work done on the gas. Right? I've strung together 3 different concepts without adding a lick of math. Well, except for some negative signs, but not a lot of extra algebra. And this is where the mathematics of a lot of what we're doing are not necessarily that complicated, right? I've just done the big scary integral for you. But what is a little frustrating sometimes is remembering, okay, because the temperature isn't changing, there is no change in the internal energy, or because the volume is not changing, there is no work being done on the gas, or the last process that we're going to talk about is called an adiabatic process, which by definition is when there's 0 Q exchange, 0 thermal energy exchange, but we'll get to that in a second. Question. The pressure of a gas must remain constant for work to be done on the gas, true or false? Good. This is a false statement. What must happen for work to be done on the gas? What must happen for work to be done on the gas? Not necessarily, because in an isobaric process, we had work done on the gas. So pressure can be constant and still work having been done on the gas. Volume has to change for work to be done. Volume has to change for work to be done, meaning the pressure could be constant, it could change, either way, but the volume must change. The volume of a gas must change. That should be if work is done on or by the gas, which I just answered this question. So yeah, this is true. Work must, if work is done, volume must change. In an isothermal process for an ideal gas, how does the work done by the gas relate to the heat added to the system, or the energy added by heat to the system? All right, the correct answer is that the work done by the gas is equal to the heat added. It is not the last one. The volume changes, so work must be done if the volume changes. And if you put this one right here, my guess is that, be careful here. What we said on that slide was the work done on the gas is equal to minus the thermal energy pumped into the gas. But this question was asking the work done by the gas, which is minus the work done on the gas. So minus a negative is the same as the thermal energy pumped into the gas. So for an isothermal process, you are effectively exchanging thermal energy pumping in to work coming out of the system. Or the other way around is for whatever work you're doing on the system, you are getting thermal energy out from that system. During an isobaric expansion of an ideal gas, which describes the work done by the gas. Good. We said that the work was P delta V, so change in volume gives us the amount of work done. Very good. Heat capacities of gases. We already talked about heat capacity and specific heat in general, but now we want to see if we can come up with something about specific heat, about ideal monatomic gases. We previously introduced heat capacity as uppercase C, where Q was equal to uppercase C times delta T. And if we add energy by heat at constant volume, then you would label this as the thermal energy required at constant volume is equal to the heat capacity at constant volume times delta T. So you imagine that as thermal energy is pumped in here, because there is an insulator and there's a pin holding the piston in place, the volume is not changing. All of the thermal energy is going into changing the temperature, which in turn raises the pressure of the gas. This would be an isochoric process, in which case you would have just thermal energy coming in here. Since the work done on the gas is 0, we would have the change in internal energy is just going to be equal to Q, which is CV delta T. And taking this as a differential, you would get the specific heat capacity, just the heat capacity. The heat capacity of the gas is equal to the change in internal energy with respect to temperature. And at constant pressure, different idea. dE internal with respect to temperature. So what is the heat capacity at constant volume for an ideal monatomic gas? Looking at that bottom equation right there. What? Not 0. The internal energy changes because the temperature changes. The internal energy change is only 0 when there's no change in temperature. But here the temperature is changing because the volume is held constant. we said that internal energy is this, so internal energy is equal to 3 halves nRT, and the heat capacity at constant volume is equal to dE dt. So we want to take the temperature derivative of 3 halves nRT, which is equal to what? What is the derivative of x? 1, right? The derivative of t is 1, and so that means that the heat capacity at constant volume is equal to 3 halves nR for an ideal monatomic gas. Specific heat at constant volume is equal to 3 halves nR. At constant pressure, then you would get that the volume is expanding, that there is work being done by the gas, and don't worry about writing all of this down, but you get that C sub P is equal to C sub V plus nR, the heat capacity of an ideal monatomic, actually for any gas, any ideal gas, C sub P, the specific heat at constant pressure is equal to the specific heat at constant volume plus nR. So for an ideal monatomic gas, what is C sub P? 3 halves nR plus nR equals 5 halves. 5 halves nR. For an ideal monatomic gas, the specific heat at constant pressure is 5 halves nR. So you can store more energy during a change that is constant pressure than you can for a change at constant volume. Say that again?
So, I don't really get it. So, is this equation saying that the equal constant pressure is equal to the equal constant velocity?
C with constant volume. Yeah, the specific heat at constant pressure is equal to the specific heat at constant volume plus an additional N times R. We can store an additional factor of nR amount of energy when we're doing a process on an ideal gas at constant pressure. Because you're having to add additional energy for the gas to be able to do that work on the piston. And this is just what I showed on the notebook slide just a second ago, and what I just described for C sub P on the previous slide. The last process we need to describe, now that we have the heat capacity of a gas defined, is when a gas expands or compresses adiabatically, meaning that there is zero thermal energy exchange during that process, in which the change in internal energy by our previous definition of heat capacity at constant volume times delta T, or times dt, is equal to the amount of work done on the gas. And effectively, what you get here, you have to consider that dt gives us is related to the change in volume. So you'd have to use the ideal gas law. You can see the derivation in your book. But what you end up getting for using the ideal gas law, the equation simplifies such that PV raised to some factor gamma is a constant. So if the pressure changes, you could figure out the change in volume based on this equation. Another way to write this equation, PV to the gamma is a constant, is that P initial V initial to the gamma is equal to P final V final raised to the gamma. It's another way to state this system. And gamma is going to be equal to C sub P divided by C sub V. So that's 5/2 in R divided by 3/2 in R, which is 5/3. Again, but this is just for an ideal monatomic gas. And that's all we've got for today. I will see you guys on Thursday.